13.8 billion years ago, something happened that defies every framework our minds have ever built to understand reality. In a single, incomprehensible instant, the entire physical universe, space, time, matter, energy, and every law that governs their interactions, came into being. Not from somewhere else, not from something that came before. Simply and terrifyingly, from nothing into everything. This is perhaps the most confronting idea in all of human thought. We are creatures of cause and effect. We trace rivers to their sources, arguments to their origins, lives to the moment of their beginning. And yet, at the very bottom of existence itself, the trail of causality runs cold. The question of why there is something rather than nothing is one that scientists, philosophers, and theologians have wrestled with for as long as there have been minds capable of asking it. And still, no consensus has emerged. Some cosmologists suggest that the universe is simply self-contained, that time itself began at the moment of creation, and asking what preceded it is as meaningless as asking what lies south of the South Pole. Others propose that our universe is just one node in a vast and eternal landscape of universes, each with its own physical constants, its own history, its own fate. A cosmic multiverse so large that every conceivable variation of reality plays out somewhere within it. Still others look to the mathematics of quantum mechanics, where nothing is ever truly empty, and where the random fluctuation of a quantum vacuum could, under the right conditions, birth an entire cosmos from a momentary ripple in the fabric of possibility. Perhaps the answer lies in the cyclic nature of existence, that our universe is merely the latest in an endless succession of births and deaths, each collapsing cosmos sowing the seeds for the next in a rhythm as old as time itself, and older. Or perhaps the answer is stranger still, lurking in corners of mathematics and physics that we have yet to illuminate. In the end, we simply do not know. The origin of the universe remains the grandest open question in all of science. But what we do know, with extraordinary confidence, precision, and elegance, is what happened next. This is that story. There is a number so small that it barely qualifies as time at all. It is 5.39 times 10 to the minus 44 seconds, a unit so incomprehensibly brief that a single second contains more of them than there are atoms in 1,000 universes. This is the Planck time, named after the German theoretical physicist Max Planck, and it represents the very smallest meaningful unit of duration that our current understanding of physics allows us to define. It is the tick of the universe's first clock. The first Planck length of time after the beginning of everything is known as the Planck era, and it is a place where our understanding of physics does not merely struggle, it collapses entirely. Everything that we know about how reality works is governed by two extraordinary theoretical frameworks. On the largest scales, Einstein's general theory of relativity describes the behavior of space, time, gravity, and the grand architecture of the cosmos with breathtaking precision. On the smallest scales, quantum mechanics describes the behavior of subatomic particles and energy in ways that are deeply strange but equally precise. Between them, these two frameworks have correctly predicted the results of essentially every experiment physics has ever devised. And yet, they are fundamentally incompatible with one another. General relativity treats space and time as a smooth, continuous fabric. Quantum mechanics insists that reality is granular, probabilistic, and inherently uncertain at the smallest scales. Fuse the two, and the mathematics dissolve into infinities and contradictions. Under normal circumstances, this incompatibility doesn't matter. General relativity operates at scales where quantum effects are irrelevant, and quantum mechanics operates at scales where gravity is negligible. But during the Planck era, when the entire observable universe was compressed into a region many trillions of times smaller than a single proton, there was no escaping either. The two frameworks were forced into direct conflict, and neither could win. What this means, in practice, is that we genuinely do not know what the Planck era was like. Various candidates for a theory of quantum gravity have been proposed. Loop quantum gravity imagines space-time itself to be fundamentally pixelated at the smallest scales. Not a smooth surface, but something more like a finely woven fabric, whose individual threads only become apparent under extreme magnification. String theory reimagines all particles and forces as the vibrational modes of microscopic, one-dimensional strings, threading their way through a reality of 10 or 11 dimensions, most of which are folded tightly away. And various other proposals, from causal dynamical triangulation to asymptotic safety, each attempt in their own way to make gravity play by quantum rules. None of them have been confirmed. The energies required to probe the Planck scale directly would demand a particle accelerator comparable in size to our entire solar system. Such an instrument will not be built anytime soon. What we can say is this: during the Planck era, the four forces that govern all of modern physics almost certainly did not exist as separate entities. Temperature stood at the theoretical maximum, the Planck temperature of around 1.4 times 10 to the 32 Kelvin. A number so vast that any attempt to intuitively grasp it is doomed. And the entire observable universe was contained in a volume so small that the quantum uncertainty principle made even the most basic properties of space and time, its shape, its size, its very existence, fundamentally unknowable. The American physicist John Wheeler imagined this early universe as a frothing, bubbling quantum foam in which the geometry of space-time flickered and shifted randomly, microscopic black holes winking in and out of existence without cause or consequence. After just one Planck time, that staggering brevity of 100 million trillion trillionths of a second, the Planck era ends, and the universe begins the long process of becoming somewhere recognizable. Imagine dropping a stone into a perfectly still pond. The moment of impact is chaotic and violent, a splash of water in every direction, a tangle of turbulent energy that seems to have no structure at all. But within moments, circular ripples emerge from the chaos, expanding outward in perfect concentric rings. Order crystallizes from disorder. Pattern emerges from turbulence. In the first fractions of a second after the Big Bang, the universe performs a trick that is in some ways similar, and in other ways far more dramatic. As the Planck era gives way to what is known as the Grand Unification Epoch, the universe cools just enough for something approaching order to begin. Today, the universe is governed by four distinct fundamental forces. Gravity pulls mass together across the cosmos. Electromagnetism governs the behavior of charged particles and the propagation of light. The strong nuclear force binds quarks into protons and neutrons and holds atomic nuclei together against the electromagnetic repulsion of their constituent protons. And the weak nuclear force governs certain kinds of radioactive decay and plays an essential role in the nuclear processes that power stars. These four forces feel utterly distinct from one another, different in strength, range, and character, operating through different messenger particles and obeying different rules. But this distinctness is an illusion born of low energies. At the energies present in the first instance of the universe, Forces that appear separate at room temperature reveal themselves to be aspects of a single underlying unity. The electromagnetic force and the weak nuclear force, which seem so different today, were in fact a single unified force, the electroweak force, during the earliest epochs of the universe. This merger has been confirmed experimentally and represents one of the great triumphs of modern physics. Push the energies even higher to those present during the grand unification epoch, and current theories suggest that the strong nuclear force joins the electroweak in a single grand unified electro-strong force. Think of it like this. Water exists as liquid, solid, and gas, depending on the energy in its environment, but in each state it is the same molecule. In much the same way, the forces of nature exist in unified states at high temperatures, only separating into their distinct identities as the universe cools and energy dissipates. The grand unification epoch lasted for a period of time roughly 10 million times longer than the entire Planck era, which still amounts to a duration so short that it defies description. And yet, for all its brevity, this was a period of extraordinary complexity. The cosmos was filled with exotic particles in a state of radical identity crisis. The distinction between matter particles and the messenger particles of force was blurred. Quarks and leptons transformed freely into one another under the influence of the electro-strong messenger particles known as X bosons. Matter and antimatter were created and annihilated in equal measure. There was no structure, no chemistry, no stable matter of any kind, only a seething, uniform plasma of energy and transient particles, all indistinguishable from one another in the furnace of those unimaginable temperatures. It could not last. The universe was expanding, and expansion meant cooling. Eventually, in a decisive transition that echoes the freezing of water into ice, the strong nuclear force broke free from the unified whole, and three forces became four. In that moment, something else happened too. Something that would determine the large-scale shape of the entire universe for the next 13.8 billion years and beyond. In the winter of 1979, a young theoretical physicist named Alan Guth was wrestling with a problem. He was not, at the time, working on anything as grand as the origin of the universe. He was thinking about magnetic monopoles. Monopoles are hypothetical particles, magnets with only a single pole, either north or south, without the opposing partner that all real-world magnets possess. Grand unified theories of the early universe predicted that they should have been produced in colossal quantities during the separation of forces. And yet, despite decades of searching, not a single magnetic monopole had ever been detected anywhere in the cosmos. Either the grand unified theories were wrong, or something had happened in the early universe to explain the monopole's mysterious absence. The solution Guth found that December night was so elegant, so sweeping in its implications, that he reportedly wrote in his notebook, "Spectacular realization." He had discovered a mechanism by which the universe, in the immediate aftermath of the strong forces' separation from the electro-strong unified field, could have undergone a period of exponential expansion, doubling in size not once, not 10 times, but approximately 90 times in a fraction of a trillionth of a second. To appreciate what 90 doublings actually means, consider this. Take a single sheet of ordinary paper, 1/10 of a millimeter thick. Fold it in half once, and it doubles to 1/5 of a millimeter. Fold it again, and it is nearly 1/2 centimeter. After 10 folds, it is about the width of your palm. After 30, it would reach above the atmosphere. After 42, it would reach the moon. After 51, It could bridge the gap to the sun. After 80 folds, the folded bundle would span the diameter of the Milky Way galaxy. And after 90 folds, it would exceed the size of our entire local supercluster of galaxies. This is what Guth proposed happened to the entire universe, an expansion so violent and so swift that space itself was stretching faster than light could traverse it. And in doing so, inflation solved not just the monopole problem, but two other deep puzzles that had been nagging at cosmologists for decades. The first was the horizon problem. When we measure the temperature of the cosmic microwave background radiation in opposite directions of the sky, points so far apart that in a universe expanding at ordinary speeds, they could never have been in contact with one another. We find temperatures that are identical to better than 1 part in 100,000. How could regions of the universe that have never been in causal contact have reached the same temperature? Inflation solves this by proposing that the entire observable universe was once contained within a region small enough for thermal equilibrium to be achieved, and then inflated to its current size, preserving that uniformity across the sky. The second was the flatness problem. On the very largest scales, the geometry of the universe appears to be flat, not curved like the surface of a sphere, nor saddle-shaped like a hyperbolic surface, but Euclidean, with parallel lines remaining parallel and the angles of triangles summing precisely to 180 degrees. The probability of this precise flatness occurring by chance is vanishingly small, but inflation explains it naturally. Just as the surface of a balloon appears to flatten as it is inflated, any initial curvature in the geometry of the early universe would have been smoothed away by the exponential expansion, leaving it flat to any possible observation. And the monopoles? Inflation would have diluted them across a volume so vastly larger than our observable universe that, on average, fewer than one would exist within the entire region we can ever see. Their absence is not evidence against grand unified theory. It is exactly what inflation predicts. The mechanism behind inflation is still not fully understood. A hypothetical energy field, the inflaton field, carried by a messenger particle called the inflaton, is thought to have driven the exponential expansion before decaying away and pouring its enormous stored energy back into the universe in a process cosmologists call reheating. This reheating re-energized the cosmos after the cooling of expansion, setting the stage for the creation of real, stable matter. It also inflated the quantum fluctuations of the Planck scale universe to macroscopic proportions, seeding the slight variations in density that would, hundreds of millions of years later, provide the gravitational seeds for the first stars and galaxies. In every meaningful sense, it was inflation that put the bang in the Big Bang. A trillionth of a second after the beginning of time, the universe has cooled from the unimaginable furnace of the Planck era and the grand unification epoch. Inflation has stretched it to an almost inconceivable size, and now, in a more spacious and slightly more leisurely cosmos, a new chapter begins. One governed by 3 distinct forces and populated by particles that are beginning to look, however faintly, like something familiar. This is the electroweak epoch, the period during which the electromagnetic force and the weak nuclear force remain unified as a single electroweak interaction, governing the behavior of all the matter that exists. Quarks and leptons are everywhere, the fundamental building blocks of matter, darting through a plasma so hot and so dense that no stable structures can form. They collide, transform, and annihilate, constantly exchanging identities under the influence of the electroweak force. The cosmos is, in a sense, a democracy of particles, where all identities are equally unstable and all transformations are equally possible. But there is something missing, something whose absence makes this cosmic democracy ultimately unworkable. Without mass, no particle can be captured by gravity. Without mass, no particle can be slowed, confined, or made to interact in any lasting way. Without mass, the universe is destined to remain forever a featureless blur of massless particles streaming through an empty, structureless void. The solution to this problem was proposed by several physicists working in the 1960s, most famously among them a British theorist named Peter Higgs, working at the University of Edinburgh. Struggling with the question of why particles have mass at all, and why they have such wildly different masses, Higgs proposed an elegant answer. He suggested that, permeating all of space-time, there exists an invisible energy field. Particles that interact strongly with this field are dragged through it, acquiring what we perceive as mass. Particles that do not interact with it at all, like photons, are free to race through the cosmos at the speed of light, forever massless. This Higgs field, as it came to be known, was communicated by its own messenger particle, the Higgs boson. For nearly 50 years, the Higgs boson remained hypothetical, a theoretical necessity whose existence could not be confirmed. Then, in 2012, after years of particle collisions at the Large Hadron Collider beneath the Swiss-French border, scientists finally detected it. The discovery confirmed not just the existence of the Higgs boson, but the reality of the Higgs field itself, and with it, an explanation for one of the deepest mysteries in all of physics. In the first trillionth of a second of the universe's history, the electroweak force underwent its own decisive separation, splitting into the distinct electromagnetic and weak nuclear forces we know today. As it did, the Higgs field switched on, permeating all of space and imbuing the newly separated particles with their characteristic masses. The W and Z bosons, carriers of the weak nuclear force, became extraordinarily heavy. Quarks and leptons acquired their various masses according to their type and flavor. The photon, carrier of electromagnetism, remained massless and free. This was not a quiet event. The symmetry that had prevailed throughout the electroweak epoch shattered, permanently and irreversibly. A universe that had been perfectly balanced became, in an instant, asymmetric. And it is from that asymmetry, paradoxically, that all the beautiful structure of the cosmos ultimately derives. By 1/1,000,000th of a second after the Big Bang, the universe has cooled to a temperature of around 1 trillion degrees Celsius, a figure that remains almost unimaginably hot by human standards, but which represents a dramatic drop from the conditions of even moments earlier. And in this comparative coolness, something extraordinary happens for the very first time. Quarks slow down enough to feel the full force of the strong nuclear force. Until this moment, quarks have been roaming freely through the cosmic plasma, an exotic state of matter known as a quark-gluon plasma, in which the usual rules that confine quarks inside composite particles do not apply. But as temperatures drop, the strong nuclear force asserts itself with irresistible authority, binding quarks together into the composite particles known as hadrons. Protons and neutrons are assembled for the first time. This assembly is governed by the properties of the quarks themselves. A proton consists of 2 up quarks and 1 down quark, bound together by the constant exchange of gluons, the messenger particles of the strong force. A neutron consists of 2 down quarks and 1 up. These arrangements are not arbitrary. They are determined by the requirement that the total color charge of each hadron, an abstract quantum property that has nothing to do with actual color, but which governs how quarks bind, must cancel out to zero, a condition known as color confinement. The internal anatomy of these newly minted hadrons is, however, far stranger than this simple picture suggests. A significant portion of a proton's mass does not come from its three quarks at all, but from the latent energy stored in the ceaseless exchange of gluons between them, a direct manifestation of Einstein's equivalence of mass and energy. Moreover, the quark content of a proton is not fixed. Quantum uncertainty allows virtual particles to flicker spontaneously into existence within the proton's interior, briefly changing its composition before vanishing again. What appears to be a simple three-quark system turns out, on closer inspection, to be a seething quantum sea of transient particles and borrowed energy. Meanwhile, a critical battle is being fought. The weak nuclear force, still operating with considerable power in this hot and dense environment, constantly converts protons into neutrons and back again. Protons become neutrons by absorbing an electron and emitting a neutrino. Neutrons become protons by emitting an electron and an antineutrino. The two species of hadron are in constant flux, their relative proportions shifting with every passing moment. This matters enormously. As the universe continues to cool toward the 1-second mark, this interconversion slows. The weak force gradually loses its grip, and the ratio of protons to neutrons begins to freeze. And because down quarks, the building blocks of neutrons, are very slightly heavier than up quarks, the energy landscape of the cooling cosmos favors the lighter proton. The freeze-out locks in a ratio of roughly 7 protons for every neutron. This ratio will determine, with surprising precision, the elemental composition of everything that will ever exist in the universe. 7-to-1. An unassuming number arrived at through the chance mass difference between two subatomic particles that nevertheless underpins the existence of every star, every planet, every atom in every living body. Consider that you are currently being penetrated by approximately 100 trillion particles every single second. They pass through your body, through the chair beneath you, through the Earth itself, without interacting with a single atom along the way. They have no electric charge. They carry almost no mass. They respond to only 2 of the 4 fundamental forces: gravity, which barely affects them at their tiny masses, and the weak nuclear force, which affects them so weakly that a light year of solid lead would stop only about half of any given beam. These extraordinary particles are neutrinos, and they are among the most abundant particles in the universe. By the time the universe is 1 second old, it has cooled to around 10 billion degrees Celsius. At these temperatures, neutrinos, which have been interacting freely with the hot, dense plasma of the early cosmos, begin to decouple. The universe has expanded and cooled to the point where the neutrinos' mean free path, the average distance they can travel before bumping into another particle, has grown larger than the observable universe itself. They are, for all practical purposes, free. They stream away from the interaction-rich plasma, carrying a snapshot of the universe at that precise moment, imprinted in their distribution and energies. This snapshot, known to cosmologists as the cosmic neutrino background, is, in principle, an image of the universe at just 1 second of age. It would extend our observational reach back in time by nearly 400,000 years beyond what photon-based astronomy can achieve. There is just one problem. Detecting it directly would require instruments approximately 1 billion times more sensitive than anything currently in existence. The relic neutrinos from that first second are drifting through space at extremely low energies, outnumbered by their higher energy counterparts from stars and supernovae, and interacting with matter so infrequently that catching them feels less like finding a needle in a haystack, and more like finding a specific grain of sand on all the beaches of the world. And yet, scientists have not given up. While direct detection remains beyond current technology, the indirect fingerprints of the cosmic neutrino background can be read in the large-scale structure of the universe. Those ancient particles, as they decoupled from the plasma, would have created subtle disturbances in the distribution of matter, small asymmetries that have since been amplified by billions of years of cosmic expansion into detectable patterns in the clustering of galaxies. By mapping these patterns with sufficient precision, cosmologists hope to confirm the existence and properties of the cosmic neutrino background, and with it, catch a glimpse of the universe in its very first second. The detectors that search for neutrinos today are engineering marvels of improbable design. Deep beneath the Antarctic ice sheet, thousands of sensors dangle from cables frozen into a cubic kilometer of the clearest, most ancient ice on Earth, waiting for the rare flash of blue light that signals the passage of a high-energy neutrino. At the bottom of Lake Baikal, in the depths of the world's deepest freshwater lake, similar instruments float in the cold Russian dark. Inside mountains in Japan, vast tanks of ultra-pure water serve as targets, monitored by thousands of sensitive photodetectors. These instruments were built to study neutrinos from the sun and from supernovae. But they are also, in a sense, listening for echoes of the universe's first second, a time when neutrinos were not ghosts at all, but among the most active and consequential particles in existence. In the late 1940s, a brilliant and flamboyant Ukrainian-American physicist named George Gamow assigned his PhD student Ralph Alpher the task of calculating how nuclear reactions in the first minutes of the universe could have produced the elements we observe today. The resulting paper, published in 1948, was a landmark of cosmological theory. Gamow, with characteristic mischief, added the name of physicist Hans Bethe as a co-author purely for the sake of completing a pun. The paper became known as the Alpher-Bethe-Gamow paper, or the Alpha-Beta-Gamma paper. Bethe had played no role in its development whatsoever. The theory the paper described, now known as Big Bang nucleosynthesis, remains one of the most precisely confirmed predictions in all of cosmology. Here is how it worked. By the time the universe is a few seconds old, protons and neutrons exist in their 7-to-1 ratio, freed from the interconversions of the weak force. The universe is hot enough for nuclear fusion to occur, but only just. And immediately, a bottleneck appears. The simplest possible fusion reaction is the joining of one proton and one neutron to form a deuterium nucleus, a single proton and a single neutron, bound together by the strong force. This should be easy, but in the hot, photon-rich plasma of the early universe, any deuterium nucleus that forms is almost immediately struck by a high-energy photon and blasted apart again. The photon bath is simply too energetic for deuterium to survive. This is the deuterium bottleneck, and it holds the entire nucleosynthetic process hostage for several minutes. Not until the universe is around 3 minutes old and temperatures have fallen to around 1 billion degrees Celsius does the ambient photon energy drop below the threshold needed to destroy deuterium as fast as it forms. The bottleneck breaks, and nucleosynthesis proceeds with breathtaking speed. Deuterium, once stable, rapidly fuses with free protons to create helium-3. Helium-3 fuses with neutrons or with other helium-3 nuclei to create helium-4, the most stable atomic nucleus in existence. a tightly bound package of 2 protons and 2 neutrons that is extraordinarily resistant to further transformation. The universe's free neutrons are swept up into helium-4 nuclei with remarkable efficiency, and within minutes, approximately 25% of all ordinary matter by mass has been converted into helium. The remaining 75% stays as hydrogen. Small quantities of other light elements also form during this window. Some deuterium escapes incorporation into helium and survives. Lithium-7 is synthesized in trace amounts, and beryllium-7 forms briefly, only to decay into lithium before it can accumulate in any meaningful quantity. And then, after roughly 20 minutes of furious cosmic cooking, it is over. The universe has expanded and cooled to the point where nuclear fusion is no longer possible. The nuclear furnace goes cold, and the elemental inventory of the universe is fixed: hydrogen, helium, and tiny traces of lithium. 3 elements, from which everything else in the cosmos will eventually be made. The remarkable thing is how precisely this prediction matches observation. Every measurement we make of the abundances of these light elements in the oldest, most pristine corners of the universe confirms the ratios that Big Bang nucleosynthesis predicts. The 25% helium abundance is not a coincidence. It is a calculated consequence of the proton-to-neutron ratio, the expansion rate of the universe, and the nuclear physics of the strong force. 3 things that were fixed in the first second of time, and whose influence is still measurable 13.8 billion years later. It is, in the truest sense, a recipe for a universe, written in the language of physics and confirmed by the sky above us. 38 seconds after the Big Bang is not a particularly memorable moment in cosmic history, but 38,000 years is something rather different. For the first 38,000 years of the universe's existence, it was dominated by radiation, photons and neutrinos carrying more energy than all the matter combined. During this radiation-dominated era, the behavior of the cosmos was dictated by the properties of light and energy rather than the properties of matter. But as the universe expanded and photons lost energy to the redshift of space itself, matter gradually gained the upper hand. Around this time, the universe transitioned from radiation-dominated to matter-dominated, and the scaffolding for cosmic structure began to quietly assemble. But there were, as yet, no atoms. The protons and helium nuclei that had formed during Big Bang nucleosynthesis were still separated from their electrons, ionized in the hot plasma that filled the universe. Electrons zipped freely through the cosmic soup, and photons could not travel more than a tiny distance before being deflected by one. The universe, despite being full of light, was completely opaque. Something subtle was happening in this opaque plasma, however. The competing forces of gravity and radiation pressure were driving sound waves through the entire cosmos, compressions and rarefactions rippling outward through the matter-energy soup like the rings from a stone dropped in water, but on a scale encompassing the entire observable universe. These are what cosmologists call baryon acoustic oscillations, effectively, sound waves in the fabric of the early cosmos. They would leave their mark on the universe in a way that can still be measured today. And then, around 380,000 years after the Big Bang, something changed. The universe cooled to approximately 3,000 Kelvin, still thousands of degrees by human standards, but cool enough for a decisive transition. Electrons, finally slow enough to be captured by atomic nuclei, were swept up by the waiting protons and helium nuclei in a process called recombination. In a cosmic instant, The free electrons that had been scattering photons in every direction were gone, locked into stable orbits around their nuclei. The universe, which had been a foggy, impenetrable plasma for its entire existence, became transparent. Every photon that had been trapped in that plasma was suddenly free. They flooded outward in every direction, filling the universe with light for the first time. A brilliant glow of orange-yellow radiation, the temperature of a stellar surface. This was the first light in the cosmos, and it has been traveling ever since. In the 13.8 billion years that have elapsed, the expansion of space has stretched those photons to wavelengths far beyond what our eyes can see, shifting them from visible light, through infrared, all the way to microwave frequencies. What was once a blinding flash of orange light now bathes the universe in a faint, cold haze of microwave radiation. The cosmic microwave background, detectable in every direction we point our most sensitive instruments. The discovery of this relic radiation in 1965 by Arno Penzias and Robert Wilson, two researchers at Bell Labs in New Jersey, was one of the most consequential in the history of science. And it came about almost entirely by accident. The two men were attempting to calibrate a large horn antenna for satellite communications and kept finding an inexplicable radio hiss that contaminated their measurements, regardless of which direction they pointed the device. They checked for instrument faults. They inspected the antenna for pigeons nesting in the horn. They cleaned the structure thoroughly. The noise remained. Eventually, they contacted a theoretical physicist at Princeton who had been independently predicting the existence of exactly this background radiation and realized what they had found. The universe itself was whispering to them, its first light degraded to a murmur, but still audible to those with the instruments to hear it. But the newly transparent universe, following the release of the CMB, was not a lit and glittering cosmos. Quite the opposite. With the photons gone, no longer trapped in the plasma, now streaming freely through the expanding void, and with no stars yet formed, the universe entered its darkest chapter. The Dark Ages lasted for somewhere between 100 and 500 million years. A vast epoch of cold, dark, nearly featureless hydrogen and helium gas, slowly pooling under the influence of gravity into the structures that would eventually become the first stars. And yet, even in the dark, chemistry had already begun. The conditions in the early universe, in the first 100,000 years before the CMB, were in some respects similar to those found in the planetary nebulae that form when elderly stars shed their outer layers late in their lives. In such environments, ions of helium, still carrying a surplus charge, encounter neutral hydrogen and, driven by the tremendous electronegativity of the helium ion, form a fleeting molecular bond. The result is helium hydride, the simplest possible chemical compound, and almost certainly the first molecule ever to form in the universe. The existence of helium hydride in space was predicted theoretically in 1978 and finally confirmed observationally in 2019 when an infrared telescope mounted on a converted Boeing 747 aircraft detected its unmistakable spectral signature in a nearby planetary nebula. That detection was not only a triumph for astrochemistry, it was also confirmation that the conditions of the early universe were indeed sufficient to produce this simplest of molecules, paving the way for the gradual buildup of chemistry that would, over billions of years, produce everything from water to DNA. It is difficult to overstate how profoundly dark the universe was during its dark ages. There was no light, not a single photon from a star, a galaxy, or any luminous source. Just cold hydrogen gas, drifting in the long, patient grip of gravity. slowly concentrating along the filaments of the cosmic web. The cosmic web is the largest structure in the universe, a three-dimensional scaffolding of dark matter and gas that spans the entire observable cosmos. It takes the form of vast interconnected filaments, hundreds of millions of light-years in length, that intersect at dense nodes and are separated by enormous voids, regions nearly empty of matter that can stretch for hundreds of millions of light-years in diameter. It is, when rendered by modern computer simulations, eerily reminiscent of a neural network, an analogy that has delighted and occasionally misled commentators for decades. The seeds of the cosmic web were laid during inflation, when quantum fluctuations in the energy density of the universe were stretched to macroscopic scales. Those fluctuations were imprinted on the distribution of matter at recombination, visible in the tiny temperature variations of the cosmic microwave background, variations of roughly 1 part in 100,000. They were amplified and shaped by the dark matter that dominated the gravitational evolution of the post-recombination universe, clumping first into dark matter halos, then drawing ordinary hydrogen and helium gas inward through the power of gravity. The first stars, designated population 3 stars by astronomers, in a numerical sequence that confusingly assigns the youngest stars the lowest number, were entirely unlike anything in the modern universe. Formed from gas that contained no elements heavier than lithium, these primordial giants were enormous. Estimates suggest they may have been hundreds or even thousands of times more massive than the Sun. They burned with extraordinary ferocity, exhausting their nuclear fuel in just a few million years, a blink of an eye in cosmic timescales, and died in catastrophic explosions that scattered the first heavy elements into the surrounding gas. Those elements were the seeds of a new generation of stars, and with heavier elements came a qualitatively different kind of chemistry. Heavier elements radiate heat more efficiently than hydrogen and helium, allowing gas clouds to cool more rapidly and fragment into smaller, denser clumps. The result was a second generation of stars, population 2 stars, that were smaller, longer-lived, and whose nuclear furnaces could forge elements beyond the reach of the first generation. Carbon, oxygen, nitrogen, iron, the building blocks of rocky planets and living cells, were synthesized in the cores of these stars and dispersed back into the cosmos when they died. And from that enriched gas, the third generation, including our own Sun, eventually formed. Somewhere in the first billionth of a second of the universe's existence, something deeply strange happened. Something so subtle that even today, more than 13 billion years later, its cause remains unknown. But without it, you would not exist. The Earth would not exist. Stars would not exist. The universe would be an empty, lightless void. The universe should contain equal quantities of matter and antimatter. Every particle of ordinary matter has an antimatter twin, identical in mass but opposite in charge and certain other quantum properties. When a particle and its antiparticle meet, they annihilate, converting their combined mass entirely into energy. No matter remains. The process is not destructive in any conventional sense. It is total, complete, and symmetric. In the early universe, when energies were sufficient to spontaneously create matter from pure energy, every particle of matter was accompanied by a particle of antimatter. The two types were created in perfectly matched pairs, and they annihilated one another in equally matched pairs. Symmetry was absolute, and when the universe cooled sufficiently that new particle-antiparticle pairs could no longer be spontaneously created, annihilation should have continued until every last particle was eliminated. The universe should have ended up with nothing but photons. And yet, here we are. Evidently, that symmetry was not quite perfect. At some point, for reasons that remain deeply unclear, matter gained a slight edge over antimatter. A surplus of approximately 1 matter particle for every billion antimatter particles. An asymmetry so small as to seem negligible, but sufficient when multiplied by the extraordinary density of the early universe, to leave behind the matter from which all structure in the cosmos is built. The physical principle that allows for this kind of matter-antimatter asymmetry is known as CP violation. The observation that certain processes treat matter and antimatter slightly differently. Experiments in the second half of the 20th century confirmed that CP violation exists in the interactions of certain types of mesons. But the amount of asymmetry that these observations can account for falls far short of explaining the overwhelming dominance of matter we see in the cosmos today. One tantalizing possibility involves a type of neutrino that has never been detected. All neutrinos observed in experiments are left-handed. They spin in a specific direction, relative to their motion. All antineutrinos are right-handed. But the mathematics of the Standard Model suggests this parity need not be fundamental. Some physicists hypothesize that right-handed neutrinos may have existed in the extreme heat of the very early universe, and that their decay, preferentially into matter rather than antimatter, could have been responsible for seeding the imbalance that gives us a universe of matter. If this theory is correct, then we owe our existence to the decay of a particle that no longer exists anywhere in the universe. The right-handed neutrino, if it ever was real, is long gone, vanished before the universe was even a millisecond old. But the asymmetry it left behind persists in every atom of every star, every grain of dust, every molecule of every living cell. The year is 1933. A famously abrasive Swiss astronomer named Fritz Zwicky is studying the Coma Cluster, a dense gathering of galaxies some 300 million light-years away. He is attempting to calculate the total mass of the cluster by two independent methods. First, by estimating the masses of the individual galaxies from their luminosity. Second, by measuring the velocities of those galaxies and using the laws of gravity to determine what total mass would be needed to keep the cluster from flying apart. The two answers do not agree, not by a small margin. The luminous mass he can see in the telescope is, by his calculation, roughly 10 times less than the gravitational mass implied by the galaxy's velocities. Either the laws of gravity are wrong at these scales, or there is a vast quantity of unseen matter holding the cluster together. Zwicky coined a German phrase for this invisible substance, dunkle Materie, dark matter. The astronomical community largely ignored his finding for nearly half a century. It was not until the 1970s that the reality of dark matter was conclusively established, largely through the meticulous work of American astronomer Vera Rubin. Studying the rotation of nearby spiral galaxies, Rubin found that the outer stars of a galaxy rotated at the same speed as those near the center, in direct violation of what Newton's laws of gravity would predict for a mass distribution confined to the visible disk. Planets in our solar system orbit more slowly the farther they are from the Sun, because most of the solar system's mass is concentrated at the center. If galaxies behaved similarly, their outer stars should be moving much more slowly than their inner ones. They weren't. The rotation curves were flat, constant velocity from the core to the outermost edge. The only explanation consistent with the laws of physics was that each galaxy was embedded in a vast, spherical halo of invisible matter, extending far beyond the visible disk of stars, and providing the additional gravitational pull needed to keep the outer stars on their rapid orbits. Subsequent observations confirmed this picture across essentially every class of galaxy and galaxy cluster. Dark matter is not a fringe hypothesis or a theoretical convenience. It is, to within the precision of our best measurements, real, present in our galaxy cluster, and every other structure in the observable universe. Current estimates suggest that dark matter outweighs ordinary matter by a factor of roughly 6 to 1. It is, in a very real sense, the dominant material in the universe, and we have no idea what it is. The most popular candidate is a new class of particle, heavier than any particle in the Standard Model, that interacts with ordinary matter only through gravity and possibly the weak force. Such weakly interacting massive particles, WIMPs, would have been created in the hot early universe in quantities consistent with the observed dark matter abundance. Searches for WIMPs have been conducted in deep underground laboratories, at the Large Hadron Collider, and using space-based gamma-ray observatories. So far, every search has come up empty. Other candidates include axions, extremely lightweight particles originally proposed to solve a different problem in particle physics, sterile neutrinos, and even primordial black holes formed in the first second of the universe's existence. Each has its proponents and its difficulties. The problem remains, stubbornly and fascinatingly, unsolved. What is not in doubt is dark matter's role in shaping the universe we inhabit. In the cosmic dark ages, it was dark matter that first responded to the gravitational seeds planted by inflation, clumping into halos that drew in ordinary gas, seeding the formation of galaxies, and tracing the filamentary architecture of the cosmic web. Without it, the universe we see today, with its rich tapestry of galaxies, clusters, and superclusters, could not have formed in the time available. Dark matter is not merely a mysterious component of the cosmos. It is the invisible architect of everything we can see. It is the most detailed picture ever taken of the early universe. It shows not a landscape or a galaxy or a star, but the entire sky, mapped in wavelengths of microwave radiation, color-coded to indicate temperature fluctuations of less than 1/100th of a 1,000th of a degree. It is the cosmic microwave background, and every feature in it is a relic of processes that occurred within the first 380,000 years of the universe's existence. The temperature fluctuations visible in the CMB are not random noise. They are, on the contrary, a precise record of the acoustic oscillations that rippled through the plasma of the early universe before recombination froze them in place. The angular scale of the largest fluctuations tells us the geometry of the universe, flat, as it turns out, confirming the predictions of inflation. The relative amplitudes of fluctuations at different scales tell us the ratio of ordinary matter to dark energy. The overall temperature tells us the age and expansion rate of the universe. The CMB is not just a pretty picture, it is a data-rich cosmological document, encoded in the photons of the universe's first light. 3 dedicated space missions, the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the European Space Agency's Planck satellite, have progressively sharpened our view of this ancient glow, extracting from it an increasingly precise portrait of the early universe. The standard cosmological model that has emerged from this work, describing a flat universe, approximately 13.8 billion years old, composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, is consistent with CMB measurements, galaxy surveys, supernova observations, and the abundances of light elements. It is one of the best tested models in the history of science, and yet, it contains within it a growing tension. The rate at which the universe is currently expanding, the Hubble constant, can be measured two independent ways: by studying the CMB and the early universe, and by studying the distances and recession velocities of galaxies in the local universe. Both methods are precise, and they give different answers. The discrepancy, known as the Hubble tension, has been growing over the past decade as measurements have become more precise, and it is now significant enough that it cannot easily be dismissed as experimental error. Whether the Hubble tension represents a flaw in our understanding of the early universe, a systematic error in distance measurements, or a genuine hint of new physics beyond the standard cosmological model, remains one of the most actively debated questions in modern cosmology. It is a reminder that, for all the extraordinary success of our understanding, the universe continues to surprise us. In 1998, two independent teams of astronomers studying a particular class of stellar explosion known as Type 1a supernovae made a discovery so unexpected and so disturbing that it upended the foundations of cosmology. Type 1a supernovae occur when a white dwarf star, the dense, Earth-sized remnant of a sun-like star at the end of its life, accumulates enough mass from a companion star to trigger a runaway nuclear explosion. Because this explosion always occurs at approximately the same mass threshold, it always produces approximately the same amount of energy. This makes Type 1a supernovae what astronomers call standard candles, sources of known intrinsic luminosity, which can be used to measure distances across the cosmos by comparing how bright they appear with how bright they actually are. By studying the brightness and redshift of Type 1a supernova at various distances, and therefore at various points in cosmic history, the two teams expected to measure the deceleration of the universe's expansion. Gravity, acting on all the matter in the cosmos, should have been gradually slowing the expansion that began with the Big Bang. The farther away a supernova was, the more its light had been traveling, and the earlier in cosmic history it represented. And at those earlier times, the expansion should have been faster, before gravity had a chance to slow it down. What they found instead was the opposite. The distant supernovae were dimmer than expected, not because the universe had been decelerating, but because the expansion had been accelerating. Space was not slowing its outward rush, it was speeding up, and the acceleration had begun roughly 5 billion years ago, roughly coinciding with the formation of our solar system. Both teams were initially reluctant to believe their own data. The result was checked, rechecked, and checked again. Other observational methods, the clustering of galaxies, the baryon acoustic oscillations, the CMB, all converged on the same conclusion. In 2011, the leaders of both teams were awarded the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe. The agent responsible for this acceleration has been named dark energy, and it is the dominant component of the universe by energy density. But what dark energy actually is remains entirely unknown. Einstein's equations of general relativity permit the existence of a cosmological constant, a term representing the intrinsic energy density of empty space, which would remain constant as the universe expands. As space grows, more of this energy exists, providing an ever-increasing repulsive effect. This cosmological constant interpretation fits the current data well, but raises a profound theoretical problem. Quantum field theory predicts a vacuum energy from the constant creation and annihilation of virtual particles that is approximately 120 orders of magnitude larger than the cosmological constant that observations require. The discrepancy between these two numbers is the largest unexplained discrepancy in all of physics. Other models propose that dark energy is not a constant, but a dynamic field, dubbed quintessence, that evolves over time, potentially having been negligible in the early universe and growing to dominance only in the past few billion years. If quintessence is real, then the expansion of the universe may not continue at a constant rate. The future evolution of the cosmos could be very different from what current models predict. Still, others suggest that dark energy is not a substance at all, but a signal that our understanding of gravity on the largest scales is incomplete. That general relativity, so successful on stellar and galactic scales, breaks down in some subtle way when applied to the cosmos as a whole. For now, dark energy remains the deepest mystery in cosmology, a force that dominates the universe, that determines its ultimate fate, and whose nature we cannot identify. There is something that requires no special observational program, no dedicated space telescope, no particle accelerator the size of a solar system, and yet which presents one of the most profound challenges to our understanding of reality. It is a question you can ask sitting quietly in a room with nothing but a pen and paper. Why do the constants of nature have the values they do? The universe runs on numbers. The speed of light, the gravitational constant, the mass of the electron, the charge of the proton, the strength of the strong nuclear force. These constants appear in the equations that govern every physical process in the cosmos, from the fusion reactions in stellar cores to the folding of proteins in living cells. They are measured with extraordinary precision, and they are, as far as we can tell, fixed, the same throughout the observable universe, the same yesterday as they are today. But there is no equation, no deeper theory, no derivation from first principles that tells us what values these constants should have. They are, in the language of physics, free parameters, numbers that must be inserted into the theory by hand, determined only by measurement and having no obvious relationship to any other quantity in the theory. What makes this disturbing is the observation that the universe is exquisitely sensitive to the precise values of these constants. Change the strength of the strong nuclear force by a few %, and carbon cannot form in stellar cores. No carbon, no complex chemistry, no life. Change the ratio of the electromagnetic force to the gravitational force by a small amount, and stars either burn out too quickly to allow planets to develop or never ignite at all. Change the mass of the electron by a similar fraction, and atoms become unstable. Change the cosmological constant, the energy density of empty space, upward by even a modest factor, and the universe expands so rapidly that matter never has time to clump into galaxies and stars. The constants appear, in other words, to be fine-tuned for the existence of a complex, structured, life-supporting universe. The probability of this occurring by chance in a universe with randomly assigned constants appears to be extraordinarily small. Several interpretations of this observation have been proposed. One is that the apparent fine-tuning is simply a coincidence, improbable, but no more philosophically significant than any other low-probability event that happens to have occurred. Another is that the constants are not free parameters at all, but will eventually be shown to be derived from some deeper, as yet undiscovered theory that uniquely specifies their values. A third, and perhaps the most widely entertained among cosmologists, though also the most philosophically contentious, is the anthropic explanation. That we live in a universe with these constants, because only universes with these constants can give rise to observers who notice their good fortune. If the multiverse is real, And if different regions of it instantiate different values of the constants, then the fact that we find ourselves in a region compatible with complex life is not surprising. It is inevitable. None of these explanations is entirely satisfying, and the debate continues. What is certain is that the constants of nature, whatever their ultimate explanation, were fixed in the first moments of the universe's existence, and that their values determined everything that came after. Every star, every planet, every molecule, every thought. 13.8 billion years ago, the universe began. In the extraordinary brevity of the Planck era, the laws of physics as we know them did not apply. During the grand unification epoch, the forces of nature were merged into a single unified interaction. Inflation stretched the universe from quantum to cosmic scales in a fraction of a trillionth of a second, smoothing the geometry of space, diluting the monopoles, and seeding the density fluctuations that would become the cosmic web. The electroweak force split. The Higgs field switched on. Quarks and leptons acquired their masses. Protons and neutrons assembled from the quark-gluon plasma. The ratio of matter to antimatter was set, for reasons still unknown. Neutrinos decoupled and streamed free, carrying their 1-second-old snapshot of the cosmos. The nuclei of hydrogen, helium, and lithium were forged in 3 minutes of Big Bang nucleosynthesis. The universe grew dark and transparent at recombination, releasing the cosmic microwave background. Dark matter assembled the cosmic web. The first stars ignited in their hundreds of millions. Generations of stellar birth and death enriched the cosmos with heavier elements. Our sun formed from the debris of its predecessors, and around it, planets assembled from the dust. And on the third of those planets, in the accumulated richness of 4 billion years of chemistry, something arose that could ask how all of this happened. We are, it turns out, not just observers of the universe. We are the universe's way of looking at itself. The carbon in our cells was forged in a stellar core. The iron in our blood was scattered across space by a supernova. The hydrogen in our water has been here since the Big Bang. Every atom in your body has a history as old as the cosmos itself. The story of the universe is, in the end, your story. And it began 13.8 billion years ago, in the most improbable, the most mysterious, and the most extraordinary moment that has ever occurred. Everything else is what happened next.